All right, class, we're going to be talking about lecture 10 today, ionic compounds. And just as a reminder, the first exam is July 6th and July 7th. And you'll notice on the schedule that July 6th is actually when you're scheduled to watch lectures 10 and 11. But keep in mind that those lectures are on the first exam. So my recommendation would be, if you can, try and get at least one day ahead of the lectures so that you're watching lectures 10 and 11 the week, or let's see, that would be Wednesday because Friday we technically don't have class. So, so you can watch lectures 10 and 11 sometime before Monday, and that way you'll have some time to actually study that material before the exam. So yeah. And just as a general rule, if you can stay one day ahead, it's kind of nice because you can ask homework questions and stuff before it's due. Sometimes if you're right on schedule, just the way that since we're not in person and stuff, sometimes it can be a little bit too late to ask questions since the homeworks are due in the morning before the next lecture. So just something to keep in mind as you're moving forward, and hopefully after this first week you can kind of see how the class is being run and what will work best for you. Okay, so all right, let's jump into the PowerPoint here. Okay, so ionic compounds. We're going to be talking about these. So as a first little quiz, this would be like a reading quiz. If you did the reading before class, go ahead and pause the video and try and answer this one. Okay, so sulfur ion, and we'll be talking about this a little bit more. But when an element is in its anionic form, right? So anionic, this is a negatively charged ion. Sulfur is towards the right on the periodic table, and we talked about how elements will want to either gain or lose electrons to get to a noble gas electron configuration. So sulfur, because it's 2 away from a noble gas, it's going to want to lose 2 electrons, or sorry, it's going to want to gain 2 electrons in order to get to the noble gas configuration. So it's going to be an anion. Okay, so sulfur anion would be sulfur with the 2 minus on it. Okay, and when you have an anion, then the ending is going to be IDE. Okay, and we'll talk about some of these coming up as well. Okay, so let's get a big picture about ionic compounds and compounds in general. So we'll be talking, we're focusing on ionic compounds in this lecture. The next one will be on covalent compounds. So we'll talk a little bit about covalent compounds because it's good to see how they differ from one another. Okay, so when you have a nonmetal and a nonmetal, right, there's a lot of different types of compounds you can make, and we'll see that coming up. Also, they exist in a lot of different phases: gas, liquid, solid. Polar and nonpolar is a term that we'll be talking about as well. But there's a lot of different options when it comes to nonmetals with other nonmetals, and it has to do with sharing electrons versus transferring electrons, which we'll see with ionic compounds. When you have a metal plus a nonmetal, these are generally referred to as salts. Okay, and they're brittle solids and have high melting points, and they have a fixed ratio of elements. So if you're going to mix magnesium and chlorine together, there's one thing you can make, and that's magnesium chloride, 1 magnesium atom for every 2 atoms of chlorine. Whereas if you're mixing carbon and hydrogen, right, there's a ton of different options that you can get. So hopefully this will just help as we start to see the difference in different compounds that can be made. Okay. So again, octet rule is kind of the basis behind a lot of what we're going to talk about, and that is that noble gases generally have 8 valence electrons. So, like I said, most atoms and elements want to either gain or lose electrons, and we'll talk about when they share electrons as well, but gain or lose electrons in order to obtain a noble gas configuration. So most of them want to have, what you'll hear people say is like they want to have a full octet. Okay, they want to have the octet filled. And what that really means is besides helium and hydrogen, which can only have 2, or hydrogen has 1 valence electron and helium has 2 valence electrons, all the other noble gases are going to have 8 valence electrons, okay? So that's the goal for other elements, is to also have 8 valence electrons. And that's why they will either gain or lose electrons in order to do that, or share electrons, which we'll talk about coming up as well. Okay. So only the S and P sublevels matter here. You could just remember that. The reason is that for argon, there is, if you look at argon, there are no electrons in the 3D orbitals, the 3D sublevel. So the only valence electrons that it has are actually found in the S and the P sublevels. And same thing with all the noble gases. Basically, this is going to happen, right? Even as you get down further, the S and the P are the ones that matter. The 3D isn't considered a valence electron because the 4th energy level is the outermost energy level, or the valence energy level. So the S and P really only matter. But basically, from this side, just understand that most atoms and elements are going to want to have 8 valence electrons. Okay. So we're looking at ionic versus covalent bonds here, and this is where they really differ. So ionic bonds here on the left will either lose or gain electrons in order to bond. So if we have a metal here, so this could be like sodium or potassium or something, right? Sodium, potassium, all those elements in the first row, they want to lose 1 electron, because when they lose an electron, they achieve a noble gas electron configuration, right? And this stands for non-metal, right? But this could be something like fluorine or chlorine or bromine or something, right? Those ones generally have 7 valence electrons. So they want to gain an electron in order to achieve a noble gas configuration. So this is a very favorable interaction here, okay? This metal loses an electron, the non-metal gains an electron, and by doing that, you form charges, right? If you add an electron to the non-metal, you're going to have a negative charge. And if you lose an electron from a metal, you're going to have a positive charge. Well, then these are going to attract, just like you'd imagine, like a magnet or something, right? Positive and negative attracting. And that bond that's formed between those two is called an ionic bond, because you have 2 ions. Remember, ions have the charges. So you have a positive, or your cation, and then you have the negatively charged ion, which is your anion, okay? And those two are going to come together and form an interaction, which we call a bond, okay? The other possible way for 2 elements to bond together is through a covalent bond, okay? So far we've talked about how non-metals want to gain electrons. Well, if you put a non-metal next to another non-metal, because they both want to gain an electron, neither one of them is going to actually give up an electron to the other, right? Only metals are willing to give up their electrons, like you see here. So instead of doing that, they're going to share, right? How nice. This non-metal says, I want another electron. And this one says, I want another electron. And so they choose to share these 2 electrons between each other, right? So here you have 7 electrons around this nonmetal and 7 around this nonmetal. Well, if you share those 2 electrons, you still have a total of 14 electrons between these two. But if you bring them together, each one of them, if you look at each one individually, right? So this nonmetal has 8 electrons around it, 8 valence electrons, so it satisfies the octet rule. And this nonmetal has 8 valence electrons around it, so it also is satisfied by the octet rule. But in order to do that, they had to share electrons. So sharing electrons forms a covalent bond. And then when you're transferring electrons and forming charges because of it, that's an ionic bond. So those are really the 2 differences there, okay? All right, and then this just kind of talks about the ionization energy, which we talked about, where metals will lose electrons. We saw that right here. And the non-metals are going to gain electrons or share them in the case of a covalent bond in order to fill their octet. Okay, so that's really the goal behind all these, is to fill your octet or achieve a noble gas configuration, and that's what drives the bonds to happen. Okay. Okay. So predicting the charges, right? We want to know, how can we, if we just look at an element, how can we know what the charge would be? Okay, so we talked about this a little bit before, but in the first group, all of these want to lose an electron. When they do that, they achieve a noble gas electron configuration. So they want to lose an electron, okay? They lose an electron, they move over to the noble gas configuration. And by losing 1 electron, they become positively charged. Same thing as you move along. Sorry. In the second column, they want to lose 2 electrons in order to get to the noble gas configuration. So that means they're going to generate a 2 positive charge, a 2 plus charge. On the right side of the periodic table, you have your non-metals, right? So these are the metals on the left side and the non-metals on the right side. And in order to achieve a noble gas configuration, if you're in the 7th or 17th, but we say 7th, 7th group here is to gain an electron. By doing so, you achieve the noble gas configuration. Okay, so you add an electron. Okay, and that gives you a -1 charge. For the ones in the 6th column, right there, 2 away from the noble gases, so they're going to need to gain 2 electrons in order to get the noble gas configuration. So they have a 2- charge. And then the same thing, 3rd over, they're going to gain 3 electrons in order to get to the noble gas configuration. Okay, so you can see that the valence electrons really plays a role. So if we look at fluorine, chlorine, bromine, iodine, right, all these halogens, they have 7 valence electrons. If you remember, this number up here really just tells you how many valence electrons they have quickly without going through the whole electron configuration thing. So fluorine has 7 valence electrons. So you can just think, okay, well, noble gases have 8, and that's what everyone wants. So if I take 8 minus whatever fluorine has, 7, that means it needs 1 to get there. So it's going to have a -1 charge. Anyway, there's a lot of ways to look at it. But yeah, basically how it is. Okay, so over here on the left of the slide, we're going to start talking about naming different compounds, okay? So cations will just keep the same name. So lithium is the name when you see Li, right? That's the name of that element, is lithium. If it's lithium with a plus charge, it's still lithium, okay? You might add the word ion in there or something, but it's just lithium, okay? Sodium is sodium, and on and on. Anions, like we talked about in the first quiz, they actually gain the IDE ending, okay? So fluorine would turn into fluoride, or chlorine into chloride, or oxygen into oxide, okay? So because they have the negative charge, their name gets changed. All right. So we'll talk about formulas now, and looking at ionic bonds and how we write out the formula, and also we'll talk about how to name those different formulas. Okay, so the first symbol, or elemental symbol, is going to be the positive ion, and then you're going to have the symbol of the negative ion, okay? So as an example, if we look at, if we look at sodium and chloride, right? Sodium is the metal, which means it's going to be losing its electron. And after it does that, it becomes a positively charged sodium. Chlorine is the nonmetal. It's going to gain an electron, so it becomes a negatively charged chlorine, okay? You can see that over here. So the positive ion is written first. That's why you see the sodium here. And then the symbol of the negative ion is written next, so chloride, okay, or chlorine. Awesome. Okay. And then one thing also to remember with your ionic formulas is that the total charge needs to be electrically neutral, okay? The salt needs to be electrically neutral. So your positive charge and your negative charges need to equal each other. Here it's easy because sodium has a positive 1 charge and chlorine has a negative 1 charge. So those equal each other, right? We have 1 positive and 1 negative charge. They cancel out and you have an electrically neutral ionic compound, okay, which is what needs to happen. The other thing to mention here, let's see if we're going to talk about it. Okay, sorry, coming back. So we said that the cation or the positive ion has its same name. Sorry, so sodium. So when you're naming the compound, you put the name also first of the positive ion, which is sodium, and then the name of the second, which in this case is actually chloride, because the chlorine has a negative charge on it, okay? So that's something to remember. Okay, let's try one that's a little bit more complicated. So you're going to use subscripts sometimes to indicate how many of each ion you have. So if you look at magnesium and chloride, magnesium is in the second column, so it has 2 electrons, 2 valence electrons that it can give up in order to achieve a noble gas configuration. So it'll give up one of those electrons to this chlorine, right? Another to that chlorine. So when it gives up its electrons, we have magnesium 2 plus, okay? And when the chlorine gains an electron, it's a chloride with a 1 minus charge on it. So to combine these two, right, I can't just write MgCl. Like up here we wrote NaCl, it was simple. But if I wrote MgCl, then I have a 2 plus charge with a minus 1 charge. So if I add those two together, I don't get 0, right? I don't get a neutral compound. In order to cancel out the 2 pluses that are on magnesium, we're actually going to need 2 chloride ions to do that. So we'll add a subscript down here, a 2, which shows that for every 1 magnesium atom or ion, we have 2 chloride ions, okay? And that's what you see over here as well. And then the name is just going to be the name of the positively charged ion, so magnesium, and then the name of the negatively charged anion, okay? And you don't need to say like, you don't need to indicate that there's 2 chlorides because you know, you will know, or you are going to practice, and so that at some point you will know that magnesium always generates a 2 plus ion and chloride always generates a negative 1 ion. So just by this name alone, you'd be able to write the formula MgCl2 because you know you need 2 negatives for every 1 positive. You need 2 negatively charged chloride ions for every 1 magnesium positive ion because there's a 2 plus charge on the magnesium. So that'll come with some practice and stuff, but yeah, that's how you do that. So that's naming the ionic compounds and coming up with their formulas right there. Another way you'll see this done is people will do like the cross method. So they'll draw magnesium chloride down here, and then they cross the superscripts. So since you have a 2 up here, that means you'd have a 2 down here. And since it's a 1 negative, you'd have a 1 right here. And since you don't actually put 1 when there's only one of them, you would just rewrite it as MgCl2. So it's another way to do it. You might see that if you watch like Khan Academy videos or something like that. It's another method people use, but it's up to you. Okay. All right, so go ahead and pause the video, and at this point, try and write the formulas and the names for all different compounds between these 5 elements, okay? All right, coming on back. So we'll work our way through this, right? So we have sodium and bromide, right? So sodium is a +1, bromide's a -1. So that means we can just write these as 1 to 1, and the charges would cancel out, okay? So we got a sodium bromide. And you write the name of the positive ion, which is sodium, and the name of the negative ion with the IDE ending. So you get the bromide, sodium bromide, okay? All right, for the next one, we have sodium with a plus charge and sulfur with a -2 charge. That means we're going to need 2 sodiums for every 1 sulfur, right? 2 positive charges because we have a -2 charge here on the sulfur. So we'll write the subscript 2 right after the sodium, which indicates there's 2 sodiums for every 1 sulfur. And then again, the name is just the name of the positive ion followed by the name of the negatively charged ion with the IDE ending. So sulfur goes to sulfide. Okay, and then last, you're going to need 3 sodiums for every 1 nitrogen because nitrogen has a -3 charge and sodium is a +1. So subscript 3 on the sodium, and you have sodium nitride, okay? Going the other way, so we have aluminum with a 3+ charge, bromide with a -1 charge, so we need 3 bromides for every 1 aluminum to make the compound electrically neutral, okay? So we have the subscript 3 and name of the positive ion and the name of the negative ion with the IDE ending to name it, okay? So hopefully these are pretty straightforward. You can work through these. We're going to talk about a few exceptions to ionic naming coming up here. Go ahead and pause the video and try this quiz. Okay. So when you tried this quiz, you probably got a little confused, and that's because I'm trying to illustrate a point here. So if you looked up tin, which is SN, on the periodic table, you're going to see that it's not in the first column and it's not in the second column, which means we haven't talked about how to know the charge of tin. You know the charge of chlorine, right? Chlorine is always a -1 charge, so it's chloride at this point, okay? But tin actually has a couple different charges it could be. So pretty much all the metals that are in that middle D block or that transition metal block on the periodic table can actually form a variety of ions. The ones in the first and second will only form, the ones in the first column only form +1, positive charged ions, and then the elements in the second column only form +2 charged ions. Okay, so we can easily do that. But when it's a metal that's in the middle block there, or I think tin's actually to the right of the middle block, but still, it makes it hard to predict the charge, okay? And we'll talk about it right here. Okay. So you have the elements in the first column and second column with the 2+ charge, and those we got down, right? We know those now. All these other ones that you'll see, and there's just a few highlighted here, but these could have, chromium, for example, could have a 2+ or a 3+ charge. Let's see. Copper could be a +1 or a +2 charge, okay? So with a few exceptions, right? So these 3 elements right here are some exceptions where the charges are actually fixed, and like aluminum, it's always +3. So those ones that we would know off the, we could memorize those charges or whatever. But all the other ones, we don't really know, okay? So if it's an element that has an ambiguous charge, you don't really know what it could be, then you have to write it in when you write the name. And we'll talk about that hopefully in an example coming up here. So the way you do it is if you're referring to chromium 2+, you put a 2 in the Roman numerals right following chromium. Or copper, if you're saying copper, you need to specify if it's copper 1+ or copper 2+, and that you do that with these Roman numerals here, okay? So if I was given this compound, iron chloride, right? Iron can have two different charges. It can be a +2 or a +3. So if you're given a compound, you can actually come up with the name, right? Because we know that chloride is a -1 charge. And since there's two chlorides here, that means this iron is actually going to be an iron with a 2+ charge, okay? And we have a chloride with a negative charge on it. So we knew this was iron +2, or iron 2+, because we have two negatively charged chlorines next to it. And since we know this is a neutral compound, we can figure that out. So when you go to name it, you would write iron 2 chloride. You'd specify the iron 2 because at this point you know that that's iron 2. If we looked at the second one here, we have iron and we have oxygen. Oxygen we know is a 2- charge. It's always a 2- charge because it's 2 away from the noble gases. Okay. And if we have 3 oxygens, that means we have a total of, so if I have iron 2O3, okay, if I divide this, the oxygen at -2 apiece is going to give me -6 total if there's 3 oxygens, right? 3 times -2 is -6. So if I divide -6 by 2, I'm going to get I'm going to get -3. But if I divide 6 by 2, I get 3, which tells me that each iron has a +3 charge because I need +6 on the left side, right? I need these to balance. This should be +6, sorry. I need the left side and the right side to balance, right? So I can figure out that the oxygen is giving me a -6, and then use that 6 to tell me that each iron is actually giving off a 3+ charge. And then when I go to write the name, right, we have the name of the positively charged ion, which is iron, and it's a +3 charge, so I put the 3 in the Roman numerals, and then I have the name of the anion with the IDE ending, so iron 3 oxide, okay? Again, you only need, and you should only put Roman numerals on the elements that you don't know the charges for. So what I mean by that is only put Roman numerals on anything that's not in the first column or the second column or one of these 4 elements here, okay? These 4 you'll just have to remember. It's pretty easy. Okay, you got +1, +2, +3 as you move up to the right here, okay? 1, 2, 3. And then right under zinc, you have a +2 as well. So those should be pretty easy to memorize there. But all the rest of them, you should put Roman numerals on if they're being used, okay? And I told you, I think in the, I don't know, one of the earlier lectures that I'm only requiring you to like memorize the first 20 elements as far as the name and symbols go. So on the test, I need to update the sheets, but you'll also have the names and symbols for each element past number 20. That way, if you didn't know what Cu was or something, if you were given this on an exam and asked to give the name, right? If you didn't know Cu was copper, that'd be kind of unfair. So I'll give you that information. Okay, so let's look at this one, right? Cu3P. Okay, so Cu is copper, P is phosphorus. Phosphorus is 3 away from noble gases, so it gives us a 3- charge. copper could give us a few different charges. So let's see. Yeah, okay, sorry. Got lost for a second. Okay. So we have 3 coppers and 1 phosphorus, okay? So if the 1 phosphorus is giving us a 3 minus charge and we have 3 coppers, that means out of the 3 coppers, we're getting a total of 3 plus charge, meaning each copper is giving us a plus 1, okay? So we would write this as copper 1 is the Roman numeral, phosphide, okay? And that would be the name that we would come up with for the name for that ionic compound. Okay, so this is going to be just, you know, a lot of practicing and getting these things down, but hopefully the basic idea is there so far. And practice going from compound, so I mean, you could even, if you just find lists like this, just cover up the right side and try and write all the names for each compound, right? Or you could cover up the left side and take the names and from the name, go to the compound. So the way we do that is, let's look at this tin 2 chloride, for example. Okay, I'm going to erase. Okay, tin 2 chloride. So tin is going to be SN, chloride is Cl, and we know chloride has a -1 charge. We also know that tin has a 2 plus charge because it's given to us in the name that it has a 2 plus charge. So when I combine these together, I'm going to need 2 chlorides for every 1 tin, right? So I would just write it out like this, kind of like we did before, okay? All right, moving forward. So here's an example. Doing lots of examples here. So for iron chloride, okay, we don't know what the charge of iron is off the top of our heads because there's multiple charges it can take on. Chloride always has a -1 charge. So we have 2 chloride ions with a -1 charge, which means that, well, let's see if I can draw a line here. Maybe this helps. Okay, on the right side of the equation, we have a total of -2 because each chloride is giving a -1 and there's 2 of them. So on the left side, we're going to have a +2 to cancel out that -2, meaning since there's only 1 iron, this iron is actually giving off 2 plus charge, okay? So we figured out that it's 2 plus, so now we can write out the name, iron 2 chloride, okay, is what we would get. All right. Working through it here. There it is. All right, let's try this one. Chromium oxide. Okay, so if we split this in half, right, each oxygen is giving off -2 charge, okay? So that means we'd have a total of -6 on the right. -2 times 3 is -6. If we have -6 on the right, that means we must have +6 on the left in order to cancel or to make this compound neutral. And because there's 2 chromiums that give us a total of +6, each chromium individually would give us a 3 plus charge. Okay, and then the oxygen is the 2 minus charge. All right. So at this point, this is kind of where that cross method is kind of useful. Okay, so if I draw CRO, and I'm trying to figure out what the subscripts are, sometimes it's a little hard to visualize in your head that you need to go up to like the least common multiple of these two, which is, anyway. So at this point, I think it is easier to just cross over the numbers. Okay, so the 3 would go on the right and the 2 would go on the left, and you can work that out, but this is what you'd get. Oh, well, we already wrote that, sorry. Well, that's good information. Okay, what we really needed from all this is just to figure out that the chromium had a 3 plus charge, because then we can write out the name. Okay, chromium 3 oxide. Okay, there it is. Awesome. Okay, polyatomic ions. Okay, this is another big big idea from this lecture. And it'll look overwhelming at first, and although there is a lot of information, it's not as overwhelming as it looks at first glance. Okay, so polyatomic ions are basically it's when you have more than one element that's giving you an ion. So far we've looked at just ions of chlorine or ions of sodium or something. And so you have a charge on a single element. A polyatomic ion is actually covalent compounds between elements that have an overall charge on them. Okay, so here's a couple examples, but you have ammonium. Okay, so this is nitrogen and hydrogen together, and they're forming covalent bonds. There's covalent bonds between the nitrogens and the hydrogens, but overall there is a plus formal charge on this molecule. Hydroxide as well, you have an oxygen and a hydrogen that are bound together that overall have a negative charge coming off of that whole molecule, okay, instead of just a single element. So that's kind of the idea behind polyatomic ions. So what we need to know from these is how to name these, okay? Here's a bunch. This is only a few of the ones that we'll need to know how to name. But we're going to talk about the easier way to name some of these. So a lot of these you're going to see is like nitrogen or carbon or phosphorus followed by a different number of oxygens. Okay, I'll give you a charge. All right. So here's how we're going to go through memorizing these. This is a table that you'd find in your book, and it has some of the ones that you need to memorize. It has most of them, but what you need to memorize, you need to know, well, you really need to know all of the ones on this table. But these ones that end in ATE, okay, so like nitrate, right, or chlorate. I don't need to circle these because they're already bolded, but these are kind of the base for other polyatomic ions. Sorry, I'm not saying this very clearly. The next slide will probably show this better, but so there's a number of different polyatomic ions that you can get from nitrate. That's kind of what I'm saying. So one is shown here. If you lose an oxygen, it becomes nitrite, okay? And so it looks like there's a lot of polyatomic ions, but a lot of them are just like related to each other. So let me go over this. So this is how you name the polyatomic ions. What I do is I find the 8 form, okay? So I memorize the 8 form of all the polyatomic ions. So you'd have like carbonate. So I'll just write down all the ones that you would need to know. So you need to memorize carbonate, you need to memorize sulfate, phosphate, you need to memorize chlorate, bromate, and iodate. And these chlorate, bromate, and iodate they're all pretty much the same. You just, since they're all halogens. And I think that's pretty much it. Okay, you also need to know hydroxide, ammonium, and acetate. Okay, those are the only ones I can think of right now, so those are the ones I'm going to hold you to. Okay, so those ones you'll need to memorize what they look like. Acetate, ammonium, and hydroxide, those are all kind of one-off polyatomic ions, okay, but all of these have different forms. So once you memorize the 8 form, you can get to all the other ones. So if you know the 8 form, so for chlorate, you would just memorize ClO3 with a 1- charge. You can get up to perchlorate by adding an oxygen, okay? If you lose an oxygen, you go down to chlorite, And then if you lose 2 oxygens from chlorate, you're going to go down to hypochlorite. Okay, so this is kind of like hypo is under, right? This would be like hyperchlorate, but they just say perchlorate. And then you have the ites at the bottom and the eights over here at the top. Okay. Again, and the charges never change. So if you lose or gain oxygens, the charges don't change. So that's what you got to remember. So you can apply this same principle for all these. So let's say, let's look at sulfate, okay? So by the time you take the test, you'll have memorized that sulfate is SO4 with a 2- charge on it, okay? So the question may not ask for sulfate, but it might ask for like sulfite, okay? Well, to go down to sulfite, we just need to lose an oxygen. The charge stays the same, and we have sulfite, okay? Or maybe it asks for persulfate. Okay, well that means we're just going to gain an oxygen and the charge stays the same. And then if we went down even further, we'd have SO2, 2-, and that would be hyposulfite. Okay, so you can see that they're all pretty much the same. Then the only other thing you need to remember is sometimes there's a hydrogen added to these. So if you add a hydrogen, so for example, if it was SO4, by adding a hydrogen, you're actually adding a positive charge. So this just becomes, it goes from -2 to a -1. And all you do is add the word hydrogen in front. Okay, hydrogen sulfate. You can also write this as bisulfate, but I will accept either answer, but you may see it written as bisulfate in homework and stuff. Okay, so if you add a hydrogen, you just put the word hydrogen in front of it and you're good. As far as the formula goes, you put a hydrogen in front of the formula and the charge is reduced by 1 to account for that hydrogen, okay? All right, hopefully that's not too bad. But focus on memorizing the 8 form of all these. And then acetate, ammonium, and hydroxide are just kind of one-off. You just memorize those 3 as well. And then, so if you know the 8 form and you know these rules, you can get to a variety of different polyatomic ions. Okay. So these polyatomic ions are going to be mixed in with ionic compounds. Okay. So we know that nitrate, you'll memorize this, is NO3-, right? And then we know that sodium forms a positive 1 ion. So to put these together, it's pretty simple. Sodium nitrate, right? It's a 1-to-1 ratio. Then you might have potassium sulfate. Okay, so potassium has a +1 charge. Sulfate is SO4 with a 2- charge. So you need 2 potassiums for every sulfate, right? So you're going to do a potassium, subscript 2, and then put your sulfate here afterwards. Applying the same principles, if you need to put multiple polyatomic ions, you need to put parentheses around the whole thing and then put your subscript. For potassium, like the one above here, the 2 just applies to the K, right? But here, if we're given the name iron 3 bicarbonate, okay, so iron is Fe3+, right? We know that because there's the 3 here. And then bicarbonate. Remember, bi just means hydrogen, so this would be hydrogen carbonate. So carbonate is CO3 2-, and since there's a hydrogen on it, it would just be a 1-, okay? So for this, we actually need 3 bicarbonate ions for every 1 iron ion, right? But we can't just put a 3 here or else it would look like 33. So what we have to do is take your iron and then actually put parentheses around the whole bicarbonate and then drop a 3 outside that so that it doesn't look like 33. This way you can tell 3 bicarbonate molecules for every 1 iron molecule. Okay. Okay, so this is hydrogen carbonate. Again, I said you can use bicarbonate or hydrogen carbonate, doesn't matter. All right, ammonium phosphite. Okay, so ammonium is NH4 with a positive 1 charge. Okay, and then so we're combining 2 polyatomic ions here, right? Phosphite is going to be PO3 with a 3 minus charge. Okay. And again, these are things, so you'll just need to know these. You'll need to know phosphite. And the way to do that is phosphate is PO4, 3 minus. So phosphite would have 1 less oxygen. Sorry, PO3, 3 minus. Again, that's something you need to work on memorizing. So here we need 3 ammonium ions for every 1 phosphite ion, and that's why we have the parentheses around the ammonium, the 3 outside, and then you have your phosphite molecule or phosphite ion. All right, sounds good. These slides again just go over the patterns, right? So from phosphate to phosphite, you just lose an oxygen, but you have the same charge. Okay. Anytime you have an 8, when you're going to the ite form, you lose 1 oxygen, but you have the same charge. And then if you're adding hydrogen, you can do bi or hydrogen, and the charge is reduced by 1. So here you see with phosphate, 3 minus, if you add a hydrogen, you actually have biphosphate, so 2 minus. Okay, carbonate, we've seen this one. Okay. All right. And then I talked about how all the halogen polyatomic ions follow the same pattern. So chlorate, so for chlorine, bromine, and iodine, very similar, okay? So if you look here, you have your chlorate, your bromate, and your iodate. Okay, these are the ones that you need to memorize, but they're all pretty much the same, right? ClO3 with a -1, or it's BrO3 with a -1, or IO3 with a -1. Those are all the 8 forms. And then if you gain an oxygen, the charge stays the same. You have periodate. If you lose an oxygen, the charge stays the same. You have iodite. If you lose 2 oxygens, you have hypoiodite, right? Losing 2 oxygens, the charge stays the same still. And then the iodide, right? This is just what we talked about before. If you have a single element that's negatively charged, it just has an IDE ending on it. Okay. Cool. All right, let's try this. Go ahead and pause your video and see if you can work this one out. If you haven't memorized, bromate and hypoiodite yet, that's fine. But go ahead and try and work this out. All right, so sodium we know has a positive 1 charge, okay? Bromate is going to be BrO3 with a -1 charge, okay? So this is just a 1-to-1 ratio, so the formula should be pretty simple. Sodium bromate, okay? All right, and then iron 3 hypoiodite. Okay, so iron has a 2+ charge. We know that because it tells us right here. And then the hypoiodite, right? So I always have to go through this in my head because I just memorized the iodate. Okay, so iodate is IO3 with a -1 charge. And then if I went down 1 oxygen, that would be the iodite. If I went down another oxygen, that would be the hypoiodite. Okay, so this is my hypoiodite. Okay, so it's IO with a negative charge on it. And I need 2 of these for every 1 iron that I have. Okay, so I'm going to say iron, and then since I need 2 of these molecules, I actually have to use parentheses because it's a polyatomic, right? And then a subscript 2 to signify that I have 2 hypoiodite molecules for every iron atom. Perfect. Awesome. Okay. All right, that's the end of that lecture. A lot of information, I know, in that one. But I think if you sit down and kind of work through it, that you can see it's not hopefully too much to digest. but really get those ionic compound naming structures down. And in the next lecture, we're going to talk about covalent compounds, and then we'll have a handle on both of those. So as always, if you have any questions, come to office hours or email me, and we'll get them worked out. All right. Have a good one.